and I'm the principal consultant at Stratiform, where we offer technical management and architectural consulting. We're based in London, but have work all around the world with an international team. And if you want to learn more, you can head over to stratiform.io, which has more information about our architectural consulting services. We have more to come in terms of management consulting as well. Feel free to contact me through the website, and also just come talk to me after the meetup, of course. But today I'm here to talk about data architecture, and specifically the architecture that I've been working on over the past couple of months. I've always worked with more common architectures and wanted to explore the world of less common ones. And for some industries, you have to be extremely creative with the structure of the data that you present to them. In the healthcare industry, for example, the storage and transmission of patient information is heavily regulated. Therefore, you have to architect your app in such a way that can accommodate not only these regulations, but also be productive for software developers in order to enable the team to create a high-quality experience. A wise programmer once said, "Bad programmers worry about the code. Good programmers worry about the data structures and their relationships." And I feel like this programmer knows a thing or two about programming. So what are the properties of the data model that I've used to architect my application, and how are they different than more common models? Well, as the description of my talk mentioned, one property is a client-server model versus a peer-to-peer model. Or in other words, a more traditional client-server model is kind of like this, where let's say you have 4 different devices and you have a server. If one device wants to talk to another device, it has to send a message to the server, and then the server relays it to another device. However, in a peer-to-peer context, each device is directly connected to each other device. Now, this is, of course, better in terms of latency and often data transfer rates, but can create complications around the networking and how you actually connect these two, as well as device availability. If any one of these goes down, that part of the network goes down with it. Another property of the data architecture that I've been using is remote data storage versus on-device data storage. So on remote data storage, you can generally store your data in the cloud on beefy clusters of servers, while the opposite of that is to store your data on the local device itself. The biggest difference here is obviously the fact that you have a potential cluster of servers acting on your data, while locally you just have your own local device. But of course, there's latency and data transfer speeds to contend with as well. Another property is distributed versus peer node architecture. So a distributed architecture is kind of like React's ring architecture here, where basically each color represents a different piece of the data, and each block is a different node that is stored on. The data is spread out across various nodes multiple times due to replication, but critically, this all acts as one single data set. This one acts as one single data source, just the data is spread out across all these different servers. This is different than peer node, where all the data is just held on its own local device. It's not spread out. So if you were to add another device, the second device would just have its own data, and the first device would just have its own data. They don't share data in any way. It's not spread out across these nodes. This means you have to connect multiple devices together to pull in the type of data that you want to build a front-end application. And now there's a ton of other properties for data architecture that I'm not going to get into for this talk, and there's a ton of other properties that I'm using myself. I'm not going to get into just to keep things simple. But if you want to talk any more about these other data models and data architectures, feel free to come talk to me after this talk, and I'm happy to talk about those as well. But to recap, a more common model would be a client-server model that's maybe distributed with remote data storage. And what I'm trying to build is the opposite of that, which is a peer-to-peer model with peer node and on-device data storage. Now, of course, I'm not the first person in the world to tackle this. There's a few other technologies that offer these same type of attributes. One of them is GNU-Net, which is a mesh networking framework for decentralized peer-to-peer communication, offers link encryption, peer discovery, and a bunch of other things. There's also BitTorrent, which I'm sure many of you are familiar with. It's also a peer-to-peer application which stores each copy of the data locally. So it's on your local device, and you're connected to each other player in the network in order to share that type of data. There's GunDB, which is a real-time decentralized offline-first graph database engine. And fundamentally, all of these are great examples of this type of architecture. These all kind of fulfill the same attributes that I just mentioned before. However, they all have their pros and cons. And like just looking at this and just knowing these different models, basically GNU-Net is the closest thing to what I want to do. But an older mentor of mine once said, "You can learn C++, DirectX, and physics to make a video game engine, or you can make a video game engine and learn physics, DirectX, and C++." Now, he told this to me when I was learning how to program, and I was trying to make my first video game engine, of course, not knowing what I was doing at all. So I started looking through books of C++, looking through books of DirectX, looking through books of physics, and he's like, Taz, just throw all that stuff away. Just go make a video game engine, and you learn all those things just by doing. And funny enough, since those days, that's been my approach to learning a bunch of new technology. Just dive right in, just use it, just try to get as far as possible. Like, you have to hit those roadblocks and get through those roadblocks, and that's how you learn new technologies and new frameworks. So how would I implement the same type of data model, but with my favorite graph query language, GraphQL? Well, of course, there's a few challenges with this. First of all, my applications can be on different versions, so they can be on completely different versions, and of course, that means that their front-end requirements for each version can change. I need to gather data from multiple different endpoints, and I need to pull that all in to construct my front end. Data fetching themselves can change. Like not only the endpoints that are available, but also the return data from those endpoints can differ. And because of this, subscriptions as well. So any sort of real-time semantics can obviously differ across versions. Persistence can differ. So if I'm saving something to a different version, the same input might fail, and the error message might be different as well. And I haven't even talked about this, and I'm not going to get into it in this talk, but actually connecting each device over a network, it can be incredibly difficult in a peer-to-peer context, but that's a whole other talk in and of itself. And again, if you want to come talk to me about that after this, I'm more than happy to talk about that. But that's also an architectural challenge in this type of architecture. So GraphQL offers consistent query semantics. I mean, it's the same query that you're querying across any GraphQL server or client. It offers consistent persistence through mutations. I mean, it's all going to act the same way. Consistent real-time mechanics through subscriptions. You can just create a subscription. You can get the same subscription no matter where you're creating it. It acts the same way. And through GraphQL, we can actually provide some consistency to the inconsistent world of peer-to-peer architecture. So how would we actually handle this data fetching using GraphQL? Well, let's say we have these two devices over here, and they're connected over a network. And the device on the left creates a GraphQL query for this type of data and sends it over to the device on the right. The device on the right has that data, so it will respond back to the device on the left, and now they'd both be in sync. So they both have the type of data that they want, and they're both kind of satisfied. But let's say the device on the right updates to version 2, and the device on the left is still on version 1. Version 2 gets rid of that name field. Instead, it has a first name and last name field. So now, the device on the left, version 1, the name field would be null. That would break our first application. So how would we accommodate this in a peer-to-peer architecture that I just mentioned? Well, we'll have to add the name field back. So basically, we have to keep the name field in addition to having a first name and last name field, so that the device on the left can still maintain the same data requirements. It won't break the device on the left. And so in this way, they can both continue to be in sync. So just to recap, the architecture that I'm using with GraphQL is an append-only schema. I'm never actually removing a field at all in my schema. I'm only adding fields to that schema. And also, all my fields are nullable. There's actually no non-null fields in my entire schema. So any applications built off this model has to be able to expect a null value, and the application either has to omit that value or deal with it in another way, or basically handle that null in some way fundamentally for the front end. It can't break. You have to expect everything to be null in the entire application. Now, some of you might think this is a bit of an extreme solution to this architecture. I mean, as a front-end developer, do I really need to set these expectations that everything's a null and everything's append-only? I mean, that seems a bit ridiculous, doesn't it? Well, funny enough, this is the exact same model that Facebook themselves use. They're still on version 1 of their GraphQL API after years of having it in production. Because they still actually have some applications that still use that very first version in production, so they can't really deprecate it without breaking those applications themselves. Dan Schaefer also said at GraphQL Europe that he actually regrets adding non-nullable fields to the specification, and that all fields should be nullable. I found this quite funny and interesting that he regrets doing that himself. And of course, this not only makes sense in a peer-to-peer data model, but if you have permissions, for example, as part of your API, let's say you have permissions that are limiting pieces of your data from getting transferred over the wire, those fields are going to be null. Right? So you can't really predict at this time what your permissions are going to look like in the future. You can't really say, okay, these are my non-null fields, and they'll always be non-null. You never know what's going to be null. You don't know what's going to be non-null in the future as well. So it's actually a best practice to have these two properties, append-only schema and all fields are nullable. And it's good to have your client actually accommodate that in production, and for your clients to be resilient to things changing over time. And so I'm actually employing these same things from the very start in my peer-to-peer data model. Okay, so let's loop back to my application again. So when you just have two devices networked together, it can be relatively simple to maintain like the state across those two devices. But let's say you have all these devices connected together, and you also have a cloud component in here that's kind of syncing to each of these devices. This can get quite complicated quite quickly. So how can we make this easier? I mean, one of the main benefits with GraphQL is not only the language, but the libraries that are built around that language. And one of my favorite libraries is Apollo. I love Apollo. Apollo is fantastic. And I like it because of its modular design. You can just pick and choose parts of Apollo that you want to use. It has fantastic documentation, and it has an extremely easy to read source code that's written in TypeScript. So it's very easy to reason about where things are getting used, and very easy to follow the types of the entire code base if you have to read the code base itself. It offers co-located queries, so you can actually keep the query right next to the component that's using it, so you can easily see the data that's being consumed by that component. Has an identity cache. So if you were to pull in a node with an ID field, for example, and you're using that in one view, and you pull that out in another view, if one of those views changes that piece of data, it's updated everywhere inside your entire application. So that's quite handy. It has support for subscriptions as well, so it can support real-time semantics and all that fun stuff. So how does this work inside my application, where I have multiple different devices connected to one node? I mean, Apollo's meant to work with like a client server, only one data source. How do I get it to work with multiple different data sources all feeding into one device? Well, because of its modular design, I was able to do exactly this. I was able to just go in, grab its query manager. That's the thing that's actually managing the queries and actually making the requests and actually managing the whole identity cache and everything. And in, 16 lines of code, I've implemented a per-device identity cache, per-device co-located queries, per-device subscriptions, per-device everything. And you might be wondering what the network interface is there. That's just your standard Apollo network interface. I'm not doing anything fancy. That's just their same old simple network interface that I'm grabbing. So because of their modular design, I can just go in, grab a query manager, and bam, I have all that awesome functionality for each and every device in my application. Now, funny enough, since I built this, someone actually sent in this pull request on React Apollo. So if you're using React, you can actually just pass in a client option, and you can create multiple Apollo clients and just pass it in as an option. So you can now actually create multiple different data sources, and each React component can just use its own client instead of having one global Apollo client, one data source for your entire application. So this will clean things up even more for my application, but fundamentally, like you're able to do whatever you want because it's a modular design. So now it looks a bit more like this. I have Apollo on each and every node. Apollo handles the caching, as I mentioned, handles the querying, handles the co-located queries. Like if you were a developer working on the front end of this, it would be no different than you working on any other Apollo application. That's really the beauty of this type of architecture and this library, and I'm very proud of being able to do that. So anyway, we've talked about this GraphQL peer-to-peer data architecture, but fundamentally, this is just the beginning of a very long journey. I mean, as I mentioned, there's a lot going into the networking of these actual devices, a lot going into actually keeping these devices online, a lot going into making sure that there's as little data transferred over the wire as possible. I haven't even talked about how multiple devices in a multi-master context on the same user account sync to the cloud, for example. That can get quite tricky quite quickly, as you can imagine. But again, happy to talk about that after this, because all of those are talks in and of themselves. But I feel like what I presented here can be very useful for a large variety of applications, and I hope it makes you think about GraphQL and data architecture in a different way. Because going back to the healthcare example, if you could create a peer-to-peer network that only lives inside that hospital, if doctors share information on patients and only lives inside that hospital to the other peers that are there right now, I think that could be revolutionary for healthcare, for example, where patient health information and all the data regulation around that makes it extremely limiting on what you can actually do with patient information. So something like this could really revolutionize that entire industry. And I'm really looking forward to seeing what you're able to do now that you know all this. Thank you very much. Any questions?
I need to do a little setup, and we can you can start with some questions. I will do a little setup to use the tool.
Sounds good. Sounds good. I guess we'll just take questions from the audience. Oh, let me do that. Oh, I'm not on the internet. I'm not on the internet. A peer-to-peer network would be great right now.
Hey, Taz, I have a question.
Yes, Yanni has a question.
You kept referring to my application. Is there an actual application that you are building using this architecture?
Yes. So the question was, I kept referring to my application. I'm actually building something with this application that people can use. The answer is yes. I am actually building something with this architecture, and that's basically why I want to present today on my learnings about actually building something with this architecture. I'm not ready to talk about that application in particular yet, but I'm more than happy to talk about the underlying architecture that I've used to build it. So things like this peer-to-peer model, things like this data architecture. But fundamentally, I'm looking at ways that we can change the norm. I mean, like the norm is client server. The norm is, I have one data source and I want to pull everything from one data source. The norm is single master. The norm is, basically remote data storage. I want to explore the world of less common data architectures and see what they enable and how I can leverage that, when I'm helping to consult different clients. And I can say, oh, hey, you actually want this and this and this instead of that and that and that. Let me just put this up on the screen. Yes, at the back.
Talking about the depend-only approach, and then
So the question was around persistence in GraphQL, specifically with mutations, and how do I handle mutations which could change from version to version. Let's say you have mutation on one version, and that mutation's like it's no longer available on another version, or something like that, where you have potentially nullable fields, and like data persistence could just be quite messy in those contexts. I mean, fundamentally, like to your point, it can be quite tricky. Basically, what I found is I haven't gone with a pure append-only approach. I do have a cutoff. So I say, I have version 1, which is compatible with other version 1. So version 1.1 will be compatible with version 1. Version 1.2 will be compatible with version 1, and so on and so forth. And then version 2, you have to upgrade your app from version 1 in order to communicate to version 2. So something kind of cool that I'm playing with right now is actually a peer-to-peer update. So if you connect with another peer and they're on an old version, you can actually do a actual hot code update to them if you've downloaded it yourself, so it'll actually update their own instance of the running code themselves, so they can actually work off of the same version. But to answer your question, it's incredibly tricky. Like to your point, to the question, I mean, the way that I've done it is I set some baseline expectations about what the schema will kind of return, and then if certain mutations aren't available, I will drop down to other ones that I know that should be available for that given schema based on the expectations. Yes. Can I talk a little bit more about the problem space that inspired me to use peer-to-peer? Well, I mean, honestly, it was just that I want to do something different. I mean, I've been doing client-server so long, and I'm so accustomed to that same model. I just want to do something different, and really hearing more about decentralized peer-to-peer networking, I wanted to kind of explore that space more. And as I touched on, I wanted to build it myself so I can learn like the intricacies of actually developing this architecture on my own. Through that, I'm a big fan of actually having a use case and actually having an application, like you're actually building something that people want to use, because like I like to say, it goes back to the 90-90 rule. If you're not familiar with the 90-90 rule, it's basically the first 90% of your application takes 90% of the time. The last 10% of your application also takes 90% of the time. And that last 10% is where, basically, historically for me, I've gained the most knowledge. I've learned the most by finishing off that last 10%. And you can only really achieve that by having a real-world application in mind. So in essence, going back to your question, I just wanted to use something new. I just wanted to use something different, and that's the way I learn best. And I wanted to build something cool with it. Yeah. Any other questions? Lorenzo.
Hey, so you talked about using Apollo to make all your peers communicate with each other. What's the magnitude of clients that can use Apollo? I mean, it's just mobile devices, laptops, or IoT?
Yep, great question, fantastic question, in fact. I talked about using Apollo in order to pull in data, and I'm using Apollo with my GraphQL library to basically interact with GraphQL servers and in a client context. So basically, which types of devices can utilize Apollo, and which types of devices, I guess, doesn't make sense to use Apollo. The nice thing about GraphQL, and I hope I've highlighted this in my talk, which is that you can use it for any type of data exchange. I mean, it doesn't have to be used specifically in a client-server server model, it can be used wherever you're exchanging data. And like I really think it's provided some real consistency to the type of architecture that I'm looking to implement, where there's a lot of inconsistency just from the underlying data model itself. So fundamentally, you can use GraphQL wherever you're exchanging data. Now, where can you use Apollo? So I think it's like, for me, like in this application, like the real value of Apollo was the actual identity cache. Being able to have one view over here, and like its data gets updated, and then it also updates this view over here. Like I'm not getting inconsistent data. It's not like I go to a user's page and I edit that user, and now the sidebars is inconsistent. Like everything is completely consistent across your entire application. And for me, that was the real value of Apollo in this application. I mean, like you might have the same concerns in that you might have, different views all over your application. So like something like that, Apollo would be great. I also think like the real-time semantics of Apollo are really nice. It just kind of makes that a lot easier. Like the network interface is really nice. But fundamentally, due to its modular nature, you can just pull out whatever you want and use whatever you want. It's not like a few other GraphQL libraries that might be a bit larger and might come as one whole package. This is quite a bit more modular, so you can just pick and choose what you want to use. Yes. How do I figure out which peer to talk to? So that's all part of the network discovery protocol that I'm using, and that's a whole other talk in and of itself. But in essence, yeah, I have a peer-to-peer discovery protocol that would then notify me when other peers go online, start receiving requests, and also go offline. And a part of that peer discovery protocol is what I'm using to basically make a connection and then start transmitting some information, so schema information, version information, so on and so forth, and then kind of going from there. Yeah. Am I using multiple devices such as native devices and web or so on and so forth, or just the same, I guess, underlying platform? Right now, I'm developing off of mobile devices because I feel like on the web you have a client-server connection automatically because you have a web, but I mean, that doesn't mean you can't do it on web. What I'm using it on right now is basically mobile devices. So I have access to the underlying hardware, thankfully, so I can actually drop down to that from JavaScript and then interact with the underlying hardware to do any sort of stuff I might need to do there. But that being said, there's nothing preventing you from doing this on the web per se. You can think of your server in the cloud as just another node. Right, and in that context, you can have a peer-to-peer protocol between servers, for example. I mean, like the opportunities are really endless. Yes. Sorry, I can't hear you very well. Yeah, that's a great question. So the question was, basically, how do I handle forward compatibility? So in the case where there's a client that is looking for maybe just first name, but that data model only has name present, for example, first name would then be null in that case. So basically, how I would handle that is I would, like as I mentioned, I have like kind of a cutoff based on my versioning. So the version 1 series can only interact with other version 1 series. So like version 1.1, version 1.2, version 1.3, so on and so forth, all kind of have the same underlying expectations. So for all versions in the 1 series, for example, I would just pull everything related to name. I'd pull name and first name. And that way, I still have some underlying expectations around the types of data I'm receiving. But again, based on all fields being nullable, I have to expect first name can be null. So if first name's null, then I drop back to name, and then I split name and grab the first name and hope for the best. Like basically that's how I get around it. Oh, there's a question up here. Perfect. What are the security implications of P2P? How is authorization handled? That's a fantastic question. And basically, and that's by Mark. Mark, yes, we're going to stick with Mark. So Mark, that was a great question wherever you are in the audience. Basically, this goes back to, I forget the exact like person or theory that this is, but basically in an entirely peer-to-peer networking infrastructure, how do you trust any peer? I mean, if there's no central authority to like authorize or validate the authenticity of that peer, how do you trust any peer? And that's basically what this question is going on about, and it's a fantastic question. So basically, how I do it is, well, like I have a central authority to actually authenticate. Like you have to authenticate versus a server. That's how I get around it, and basically the networking, the peer-to-peer network itself is encrypted. So you do get encrypted communication from peer-to-peer. But fundamentally, authorization is handled by a server, and I actually authenticate with that server, and that gives me some level of trust and some level of authenticity to the entire application. Yes. Sorry, I can't hear you very well.
That you're pushing and live updating your other clients to newer versions. Is there any protection in place to essentially prevent from malicious pushes?
So that's a good security question as well. So like I mentioned, having a potential code push over peer-to-peer, and that will actually update old peers to a newer version of the application. And is there anything that will lock down that malicious type of data transfer? I haven't gotten there yet. I'm still exploring that space, to be honest with you. But I think fundamentally, because the rest of the application and its own data exchange is secure, it is encrypted, and it is trusted by the central authority, I think it should be okay. But again, I haven't really delved that deep yet. I mean, to your point, if you can do a remote code push and that can update the live running code on that application, I mean, that's a potential security concern. But I simply just haven't gotten that far yet. Yes. How am I handling redundancy across devices and device storage? So that was something I touched on a little bit. That would be a whole other talk, but happy to touch on it right now. So basically, redundancy is handled because you can have multiple devices on the same user account. So you can have, like I can have my iPhone, I can have my iPad, and they can all be part of the same user account. Knowing that they're part of the same user account, data will be shared amongst them. That is a multi-master data architecture. So when you start talking about multi-master data architectures, you have to naturally talk about conflict resolution as well. And conflict resolution is a whole crazy topic of discussion and how you actually know how to resolve conflicts. How do you merge data that is potentially, if I create something on my phone and on my iPad, how do I merge those two pieces of data? That can be quite messy, and that's a whole intricate type of process, and how do you can handle that conflict resolution. But basically, that's one way that I actually make my data redundant, is I spread it across nodes that are off the same user account. Another way is that I actually utilize a cloud service as well. So there's basically a single tenant cloud service. So a single tenant versus multi-tenant is another aspect of data architecture, whereas a single tenant cloud service is specified for that one user, and then your data on device is actually shared to that cloud service. So your data is backed up to cloud for whatever reason. But once again, you run into conflict resolution, multi-master conflict resolution amongst peer-to-peer and client-to-server. So it can be quite tricky, but yeah, if you want to look up multi-master client resolution, like conflict resolution, you'll get probably 3 days worth of academia on that. Any other questions? Yes. Have I actually done any of the things I just said? Sort of big words, Taz. Like, are you just talking or are you doing? I have created some of it, and to answer your question in terms of what I've actually done, because this is the same user, because you as a person, you've done this on your iPhone, you've done this on your iPad, you've done this on all your devices. I can basically safely bet that the newest mutation that you've done yourself, you as a knowledgeable human being have done yourself, is the latest, and therefore that should be the latest piece of data. I'm pretty much going towards CouchDB model in that, like, basically newest wins. But as you know, time can be an interesting concept on devices, and knowing which one is the latest and determining the latest in time is a whole other interesting topic of discussion as well. And that makes it a bit tricky sometimes. But to answer your question, yeah, like you can like in my specific case, because it's a single user on a single tenant, I can hopefully rely at the newest wins. More questions? Yes. I mean, yeah. So, so the question was, I said something about time. What about differences? What about devices on different time zones? I mean, you're absolutely right. That's one massive complication with relying on newest first. Is what if, like, if you generalize to UTC time, but let's say your user goes to a different time zone. Instead of adjusting the time zone on the device, they adjust the actual system time on the device to be whatever that time zone is. So now they're however many hours different than what you are compared to UTC time. That just throws a massive wrench in the entire equation, doesn't it? So I mean. You have to be very creative when dealing with what is newest first, and and all of that. So that's again a whole other topic of discussion. But that's exactly one of the issues with determining what is newest first. I think there was a question in the back. No, might have been the same one about time. There was a bit of a conflict resolution happening there. Newest first. All right. If there's no other questions, then I'll thank you all very much for listening to my talk. Thanks.